cost about 20 scores in our final examination. This score is about the strip space. This formula is about the strip space. So this is cost about 20 scores. So it's very important for us. And the another is the Maris law. Maris law is cost more than 10 scores. It's about the polarization property of light. Maris law here is this formula. So these two formula is important in this chapter. And here about the optical rotation effect is something we are concerned for medical students. So this is why we have studied this chapter, because some of the formula of medicine are concerned a connection with the wave optics. Okay, let's finally review about the last chapter, the direct current. In this chapter, we have studying some basic notion about the current. Yes, in your middle school, you have studied the knowledge for the current. So this is a definition for the current. You already know. Here we're studying another notion about the current density. Current density means which magnitude is equal to the current flowing vertically through a unit cross-section of a conductor. Why we need to introduce the current density? Because in some conductor, it's not the charge pass through this arrow is not uniform. Maybe in some part, the charge more, and in another part, the charge pass through this arrow is very small. The charge is small, and maybe in some part the charge is large, has more charge pass through this arrow. So it's non-uniform. If the conductor is non-uniform, we need to current density to show the property of this conductor. In our middle school, we do not study the current density because we just studying the uniform conductor. But in our literature, most of the conductor is non-uniform. So we need to introduce the current density. It's help us to know the property of the non-uniform conductor. And the relationship between the current and the current density is this formula. The current equal to the integral of the current density by the arrow. Drift speed. Drift speed usually is very small. Is smaller than the thermal speed. Thermal speed, the electron in the conductor has two parts of movement. One is drift speed by the voltage, by the electric field. Another is the thermal movement by the heat, by the temperature. So this is two kind of motion for the electron. but the drift speed is very smaller than the thermal speed. Usually the drift speed here is usually in this range. It's very small. And the another notion is EMF, is the electromotive force. Electromotive force is defined in this formula. Is the work done by a non-electrostatic force to move a unit positive charge from negative to positive in a battery or in a power plant. If we want to move positive charge from the negative pole to the positive pole. I mean, the pole is this. Yeah, the pole. From the negative pole to the positive pole, we need to have non-electrostatic force. Only non-electrostatic force can move the positive charge, move from the negative pole to the positive pole. Here is several kinds of non-electrostatic force, like chemical force in battery, Lorentz force in water power station, and the diffusive force in the thermoelectric power or photoelectron effect in solar cell. So this is several kinds of non-electrostatic force. Okay, the important knowledge in this chapter is about the Ohm's law and the Kirchhoff's law. The Ohm's law is our model for the Kirchhoff's law. So the Ohm's law is just a model. It's just a model for the Kirchhoff's law. Model. A model means the simplified version. So Ohm's law is the simplified version of the Kirchhoff's law. Version, is that right? Is a simplified version of the Kirchhoff's law. So let's directing to the Kirchhoff's law. What's the Kirchhoff's law? Here is the Kirchhoff's law. Kirchhoff's law contains two equations. First is Kirchhoff's force law, or called the Kirchhoff's current law. This formula means that the summation of the currents entering any junction must be equal to the sum of the currents leaving that junction. What's the meaning of junction? Junction is a connection point of three or more branches. What's called branch? Branch is an unbranched circuit consisting of a power supply or resistor or series of them. Loop, a closed path consisting of several branches, called loop. Like in this circuit has two junctions, junction A and junction B, and three branches. the upper branch, the middle branch, and the lower branch has two independent loops. The first loop and the second loop. These two loops are independent. So Kirchhoff's current law says that the sum of the current entering any junction must equal the outcoming current of that junction. The Kirchhoff's voltage law. Kirchhoff's voltage law is this formula, which told us that the directed sum of the potential difference around any closed loop is zero. The potential difference contains the voltage. The potential difference also called the voltage. The voltage contained the voltage in the resistor and the voltage in the battery. So this is the Kirchhoff's voltage law. The voltage law for a loop, for a closed loop, is zero. The physics mean of the Kirchhoff's current law is that the charge conservation. Due to cause of the charge conservation, we get the Kirchhoff's current law. And due to the energy conservation, we get the Kirchhoff's voltage law. So Kirchhoff's voltage law means that based on the energy conservation. But the thing in the voltage law is that here is a sign. This has the sign. Single or sign, I don't know if this word sing. I mean, here the voltage in the resistor we have, maybe it's positive or negative, and also for the EMF, it's maybe also positive or negative. We call this sign, maybe these words. So how to decide the positive or negative? We need symbol rules. What's a symbol rules? The symbol rules is also according to the physics in the current in this circuit. So the symbol rules first we assume the current direction and the loop run direction. These two directions are assumed randomly. Assumed random, or just depend on you. You can choose any direction for the current direction and loop direction. But when you choose these directions, then if the assumed current direction is same as the loop direction, then the voltage as a resistor take positive sign. And if the assumed current direction is opposite to the loop direction, the voltage in the resistor take negative sign. And if the loop direction is first meeting the positive plane of battery, the EMF take positive sign. And if the loop direction first meet the negative plane of battery, the EMF take a negative sign. So this is all about the Kirchhoff's law. Now this is the knowledge or content in the last chapter. The last chapter the most important content is careful snore. Okay, this is all about the content in the last chapter, direct current. Now let's discuss about the questions in these two chapters. Let's talk about the problems and the wave optics and direction current. And some of these questions will be shown in our final examination. Let's first say the question 1. This is a choice question. We have two choice questions here. Now let's say first one. One battery has an EMF of 20 voltage. And the internal resistance of 0.1 ohm. Another battery changes it with 10 ampere current, charges it, not change, charge. What's the terminal voltage at both ends of the charged battery? What's the meaning of this question? This question tells us charged battery. Here is the charged battery. The positive pole and the negative pole. Positive polar and negative polar. This is the charged battery. Not all of the battery can be charged. Some of the battery can be charged, and other battery cannot be charged. And this question tells us the physics property of charged battery. Here is the charged battery. This battery has EMF about 20 voltage, and the internal resistance is 0.1 ohm, and this battery is charged by another battery with 10 ampere. I mean, use this battery collecting current. If we want to charge this battery, what's the direction for the current? If the current is from right to left or from left to right, what's the current for the direction of the current? If we want to charge this battery, if we want to charge this battery, what's the direction of the current? Yeah, maybe you need to choose the answer. If we want to charge this battery, this is the negative polar, this is the positive polar. If we want to charge this battery, what's the direction for the current? Does the current is from right to left or from left to right? And most of you are choose the direction of the current from left to right or right to left. I don't know what I draw first. The answer is from right to left. This is the correct direction. This is the correct direction. Why? Because if we connect this material to a resistor and we connect the switch here, and okay, if we turn the switch, this material will not be charged. This material will provide power to the resistor. This material will consume its power. It's not charged. The EMF will become more and more small. So if we want to charge this material, the current must be from right to left. We can charge this material. So the direction is from right to left. From right to left, then what's the voltage and the both ends of this battery? What's the voltage? According to the symbol rule, the voltage between A and B equal to the EMF of this charged battery. Because we first touch the elective polar, so it should be minus EMF. And here AB means that our loop direction is from A to B, but the current is from B to A, so we need to minus I times R. So the answer is minus 20 minus I is 10 ampere times the inner resistance 0.1. So the answer is minus 13 voltage. UAB is minus 13 voltage. Then UBA is minus UAB. It should be 13 voltage. 13 voltage. So the answer is D. If there is an answer, if we change the answer B as minus 13 voltage, it's also right. It's also right. If we change the answer B as minus 13 voltage, it's also right. Because here the terminal voltage and both ends of this material. The question do not tell from which point or from which ends. We can let from A to B, and we can also let from B to A. So the answer minus certain voltage or certain voltage. It's also right. It's also right. But the magnitude is same. The magnitude is certain voltage. So this is our answer. Now let's say the question 2. The question 2 is about Murray's law. When a electrolyte with intensity I0 pass vertically through a polarizer with two polarization direction intersection for 60 degree. What's the intensity of the transmitted light? When a electrolyte, we can draw the electrolyte on this diagram. The electrolyte has two polarization direction with low fixed phase. With these two direction has low low fixed phase difference. They are independent. So electrolyte is make up of two linear polarized lights. These two linear polarized lights are vertical, and these two linear polarized lights has low fixed phase difference. Low fixed phase difference. This is called electrolyte. When this electrolyte passes through a polarizer, it become this is a natural light. When this natural light pass through a polarizer, it will become a linear polarized light. Become a linear polarized light. Linear polarized light. And this linear polarized light pass through a larger polarizer. The vibration direction will be changed. Here, this question asks us what's the intensity of the transmitted light. We need to use the Murray's law. We have, according to the property of the electrolyte, when the electrolyte pass through polarizer, the intensity will become half of the intensity. So if the intensity is I, when the electrolyte pass through polarizer, the intensity will become half of I. Because the electrolyte can be seen as two linear polarized light. One linear polarized light pass through the polarizer. If the polarized light, when the direction is same as the polarization direction, this part will pass through the polarizer, and the perpendicular part will be absorbed or will be reflected by the polarizer. So the larger part will be absorbed. I don't know if these words will be absorbed or reflect. So only 1/2 of the electrolyte can pass through the polarizer, so the intensity will become half. And what's the intensity of when it passes through a larger polarizer? We need to use the Morris law. According to the Morris law, the intensity equal to the incoming intensity. The incoming intensity is half of I. Is half of I, and times the cosine alpha square. Here alpha is 16 degree, which means that the polarization direction of these two polarizer has an angle of equal to 16 degree. 16 degree. So alpha is 16 degree. Cosine 16 degree. Cosine 16 degree is 1/2. So it's 1/2. 1/2 square is 1/4. 1/4. So the answer is I by 8. I by 8. So the answer is C. C is our answer. So the answer is C. And in our final examination, the last long question or long question is the calculation calculation question about the Morris law. It costs 10 scores. 10 scores in our final examination is about the Morris law. So we change the short question to a long question. It's about 10 scores in our final examination. Let's say the judge questions. If here is 3 judge questions, if there are n injections in the circuit, then n plus 1 independent junction equation can be listed according to Kirchhoff's current law. The answer is wrong. The answer is wrong. The correct answer is n minus 1 independent junction equation. Like in this chapter, here, like in this equation, we have two junctions A and B, but we only have one equations for the Kirchhoff's current law. Here we show you. So here we only have one equations. Because for the junction B, the Kirchhoff's current law is the income current equal to the outgoing current. So for the junction B, we need to write I1 minus I2 minus I3 equals to 0. And this is just the equation for junction A. So the equation for junction B is independent to this equation. They are independent. So this equation is 2 more. So this equation is 2 more for us. So this equation is not necessary. So if we have n junction in a circuit, then we only have n minus 1 equations for Kirchhoff's first law. So here for this question, for the correct answer is n minus 1. So it's false. The light has wave particle duality. Right. In Young's double-slit invariant experiment, if white light is used as light source at each maximum point, what is maximum point? In order from inside to outside. So here maximum point is the bright line, is the maximum point calling max point, yeah, corresponding to the not brain bright line, corresponding to the bright line. From inside to outside, the color strip from purple to red, except that the central bright strip are white. What's the mean? It means that if we use the white light to do the Young's experiment, we have the diagram in the screen. For the central bright strip, it's white. It's white, and for the larger order, like the first order, second order, third order, it's not white. It's colorful. The color strip is from purple to red. So purple is inside, and here purple is inside, and here purple is inside. From purple to blue to yellow to green to yellow to red. So it's colorful. When right here again, it's purple and blue and green and then yellow and then red. Why? Why the strip is colorful for the white light? Why? Because the white light is not not LED light. LED light means that it has only one frequency. The white light is not a LED light. It has many frequencies from red to purple. So white light has many frequencies from red to purple. Different frequencies has different wavelengths, because according to the wavelengths equal to the speed times period, and equal to the speed by the frequency. The speed of light is the same for red light and purple light. Is a red light or purple light also have the same speed. The speed of light is about 3 times 10 to 8 power meter second in vacuum. So it's a constant for for different frequency of light. So it's the same. So if the frequency is smaller than the wavelength is large, the purple has large frequency, so its wavelength is small. And let's put into the formula about the strip space. For this strip space, depend on the distance between the slit to the screen and multiply by the wavelength, and divided by the distance between the two slits. So here big D is the distance between the slit to the screen. Here different lambda has different strip space. Red light has larger wavelengths, so the strip space is also larger. So the red light always in the outside. Is always in the outside. For different order, this is the first order. This is the third order. This is second order. This is the third order. So for different order, the red light is always in the outside because the wavelength is large. And then for the purple light, because the purple light has larger frequency, so it has lower wavelengths. So it has the lower strip space. So it's always inside. So different wavelengths has different strip space. So when we use the white light to do the experiment, we get colorful strips. These strips from purple to red, from purple to red. So so it's right for this question. So it's right. Here, short answer question. Explain that under white light, the soap film is colorful, and when black spots appear on the film, it indicates that the film is about to rupture, about to break. This is about the film interference. Now let's skip this question. It's about the film interference. Some film interference. Actually, we have the same film interference during when we talk about the chapter of wave optics. We have told the same film interference. Actually, we have learned the same film interference, but it's not our main topic. So let's skip this question. Here, let's say about this calculation question. Here is computation question is also same. This question is also important for us in our actually in our final examination. It's actually this question. Yeah, this question is our final examination. You know. Yes. Actually, as shown in the figure, it shows that epsilon 1 is 20V, epsilon 3 is 4V. The value of the ammeter is 0.5 ampere. Where is the ammeter? Here is the ammeter. The ammeter is 0.5 ampere. Its internal resistance is neglected. Usually, the ammeter has very small internal resistance, so we neglect it, and then the current direction is showing the figure. What's the EMF of the power supply epsilon 2? What's the EMF of epsilon 2? What's the value of epsilon 2? The question just told EMF 1, EMF 3, but not tell us EMF 2. And the resistance about the resistor, this resistor is giving us 2, 4, 6. And also the current through the ammeter is 0.5, and the direction are showing the figure as from left to right. What's the EMF 2? Yes, actually we need to use the Kirchhoff's law. This question has two junctions. This circuit has two junctions. Junction A, B, and it has how many branches? 3 branches. The left, middle, right. And how many independent loops? 2 independent loops. So here is 3 branches. So we need to have 3 equations. The first equation is about the Kirchhoff's first law. According to the Kirchhoff's first law, let's say as junction B, the income current should be equal to the outgoing current. So I1 equals to I2 plus I3. This is equation 1. Here we do not know the I2 and I3, but we know I1. I1 is 0.5. This is I1 because the value of the ammeter is 0.5. So I1 is 0.5. And the other 2 equations are Kirchhoff's voltage law. For the Kirchhoff's voltage law for the left loop. For this loop, let's starting from here. From here, then our loop direction is clockwise. Then first touch the positive plane of this material, so it's epsilon 2. And our loop direction is opposite than the current, so it's minus I2 minus I2 time multiplied by the resistor. Here we write 4. So 4I2. So 4I2. because the resistance is 4 ohm. So why matters? Because the loop equation, the loop direction is clockwise, is from up to down, but the current direction is from down to up, so it's opposite. So here is minus, and because here for the ammeter has low resistance, so and there is no voltage in the ammeter. There is no voltage because the resistance is neglected. So the voltage and the two ends is same. Here, for this resistor, the current direction opposite to our loop direction, so it's minus 2I1. And here, let's first meet the electric polar of this battery. So it's minus epsilon 1 equal to 0. This is the equation 2. And this is our first equation. And the final equation is about the right loop. For the right loop, let's start from A. Yeah, we can also start from here, from this point. It's also the same. That's from A. That's from a first touch epsilon 3. So epsilon 3 positive. And minus 6I3. Minus 6I3 and plus 4I2 plus 4I2 yes, and minus epsilon 2 because the first touch the electric plane. Then it's over. The EMF3, this resistor, and this resistor, this EMF, then back to 8, so it's over. Equal to 0. This is equation 3. So here we have 3 equations. And in these 3 equations, our we want to know the value or the variable. Is that right? Variable? I don't know how to say variable. Sorry. We want to know is the value of I2, I3, and epsilon 3. These 3 variables we do not know. So fortunately, we have three equations. We can solve them. Putting to the values of epsilon 1, epsilon 3, and the value of I1, we can solve epsilon 3. We can solve epsilon 3. And here is our equations, 3 equations. And solve these 3 equations. We get epsilon 2 as 21 wattage. 21 wattage. So this is this equation tell us how to use the Kirchhoff's law to solve problem. If we want to use Kirchhoff's law, we need to write the Kirchhoff's current law and then write Kirchhoff's voltage law. For the Kirchhoff's current law, we have n minus 1 equations. N is the junction number of junction. Here, the junction number is 2. So we have only 1 equations for Kirchhoff's current law. And for the Kirchhoff's voltage law, how many independent loops in the circuit? Then we have how many independent equations. Here have 2 independent loops. So we have 2 independent equations. 1 plus 2 is 3, and we have 3 variables, I3, I2, and epsilon 2. So we can solve them. So these equations show us how to use Kirchhoff's law. And the other 2 equations, two problems. These problems about the strip space. Let's quickly say it. A light source is illuminated vertically on 2 slits 0.6 millimeter apart. So the little d is 0.6, and interference strips appear on the screen 2.5 meter away. The distance between the center of two injected bright strips is 2.27 millimeter. What's the wavelength of the incident light? Wavelength. According to the formula of the strip space, the strip space to the wavelength, the distance between the slit to the screen divided by the distance of the two slits. Here we have losing big D, and we have losing strip space. We have losing little d, so we can solve the wavelength. The wavelength equal to strip space times little d divided by big D. So the answer is 544.8 nanometer. It corresponding to the yellow light. So it's yellow light. Yellow light in this range. Maybe it's green light. Maybe yellow, maybe green. I'm not sure. But not red. Red is usually in 40 nanometer. This is red light. So the last question. Let's talk about last question is to use the Murray's law by taking the natural net pass-through polarizer with 2 polarization direction insert for second degree, adding transmit light intensity is I1. What's the intensity of the natural light? It's just just like the choose question, just like the choose question, but it's inverse. But it's inverse. It's just an inverse question of the choose question. This choose question tells us the intensity of the nature. and asking what's the intensity of the transmitted light. But this question already tells the intensity of the transmitted light and ask what's the intensity of the natural light. The answer for the choice question is C. It means that the intensity of the transmitted light, is 1/8 or 1/8. I don't know it's right. 1/8 of the intensity of the natural light. So if the intensity of the transmitted light is I1, then what's the intensity of the natural light? The answer is 8I1. So for the first question, the answer is 8I1. Just inverse. Is that right? Inverse progress of the choice question. Let's directly talk the question 2. For the question 2, when another polarizer is inserted between the two polarizer and its direction is 30 degree angle with the first two polarizer, what's the transmitted light? What's the intensity of the transmitted light? It means that when the natural light, this is the natural light. The natural light pass through polarizer, and a larger polarizer. These two polarizer has angle of 16 degree. And now we insert another or third polarizer between them. We now insert a third polarizer between them, and the direction is just 30 degree. 13 degree between with these two polarizer. Yeah. Because these two polarizer has angle about 16 degree. So it's 13 degree, and to the first one it's 30 degree, and to the second one the angle between them is also 13 degree. You know, just like this, it's 16 degree. But if the direction in the middle, so both of them are 13 degree. Both of them are 30 degree. So what's the intensity? What's the transmitted light? What's the intensity of the transmitted light? Yeah, we also use Morris law. Yes. For the intensity of the natural light, the intensity is 8I1. When it passes through the first polarizer, the intensity becomes 4I1. And when it passes through the middle polarizer, the intensity is 4I1 times cosine 30 degree square. And when it passes through the third one, we have to multiply a larger cosine 13 degree square. Because here we need also use the Morris law. So finally, the intensity for the transmitted light is 4 9/4 I1. Yes. So this is our final answer. 9/4 I1. Okay, this is all about the questions of the last two chapters. And our course for medical physics of this whole semester is over. In this semester, we learn the physics online without textbook, without sitting in classroom, without doing experiments, but we have insist to. But you have courage. You are insist to the ending of our course. So you are a good student. And I hope you can get a high score in final examination. And also hope you have a wonderful future and a wonderful life during your university. So if you have any question, we can discuss together. And if you don't have any question, let's say goodbye. Best wishes for you, and thank you for your